In this video, I'll introduce the t-distribution and t-tests. Recall that the central limit theorem-based confidence interval can be defined as a point estimate plus or minus a critical value from the standard normal distribution times the standard error. In continuous cases, one can invoke the CLT when we know the real population standard deviation, sigma. This is unrealistic as we almost never know the population standard deviation in practice. The standard error of the mean is computed as sigma hat over root n, but we need to estimate sigma. It's not advisable to use the standard normal distribution when the population standard deviation is unknown, especially with a small sample size, n. This brings us to the so-called t-distribution. The t, or student's t-distribution, was developed by Gossett in the late 1800s when he was working at the Guinness Brewery in Dublin with very small sample sizes. When we use the CLT-based approach, the standard error becomes unreliable with a small sample size. Hence, the t-distribution is a handy tool. It's a symmetric distribution centered at 0, whose only parameter are its degrees of freedom. Let's pause for a moment to introduce the concept of degrees of freedom in statistics. Degrees of freedom refer to the number of values that are allowed to vary freely in a given analysis. For example, suppose I have a sample of 3 students, and I know that their average GPA is 3.5 on a 4-point scale. The first students could have any GPA, say 3.4 and 3.8. After setting those values, the final student's GPA would need to be fixed at 3.3 to make the average 3.5. Thus, to estimate the sample mean, we would have n-1 degrees of freedom. In this example, 2 degrees of freedom. Now, moving back to the t-distribution. This is a case of a heavy-tailed distribution. When the degrees of freedom of the t-distribution tend to infinity, it converges to the standard normal distribution. But the fewer degrees of freedom we have, the heavier the tails will be, as shown in the plot here. The one-sample t-test involves a single sample with which we would like to make inference on a continuous population mean, mu. Using a hypothesized value mu0, we can define the null hypothesis as mu equals mu0 versus one of the 3 possible alternative hypotheses, depending on whether the test is one- or two-sided. The test statistic can be defined as the difference between the sample mean and hypothesized mean, divided by the sample standard deviation over root n. The test statistic follows a t-distribution with n-1 degrees of freedom under the null hypothesis. This can be used to compute a p-value. Let's look at an example. Say I performed an upper-tailed one-sample t-test to test if a population mean was greater than a hypothesized mean, using a sample size of 50. The degrees of freedom would be n-1, so 49 in this case. Assume we found the test statistic to be 2.5. The distribution of the test statistic under the null hypothesis is a t-distribution with 49 degrees of freedom. So we can compute the p-value as the area to the right of that test statistic, since this is a right-tailed test. Here it's 0.0079, which is quite small, indicating that if these means really were equal, the chances of observing a result as extreme as ours would be quite rare. We can also use a t-test to compare 2 population means. Let delta be the difference between the population means A and B. The null hypothesis can be written as delta equals delta 0, where delta 0, the hypothesized difference in means, is usually 0. We can test the null against a similar set of alternative hypotheses depending on the question at hand. Although I won't go into as much detail here, the nature of the test statistics and their degrees of freedom depends on whether we can reasonably assume equal population variances, which can be tested using something called Levene's test. To summarize, I hope I've convinced you that we need the t-distribution when the population variance is unknown, especially when the sample size is small.